Okay, so we have chapter 4.2 where we're going to learn about the natural exponential function. So we have that the natural base is represented by e, and e is actually an irrational number. E is the value that 1 plus 1 over n to the n approaches as n becomes large. So our e is actually approximately 2.718. So here in this table, we could see our n values on the left, and then on the right we have the 1 plus 1 over n to the n power. And we see we get closer and closer to 2.718. So as n goes to infinity, we have that 1 plus 1 over n to the n approaches e. So this is pretty helpful in calculus. And so in calculus, this would be just expressed as the limit as n goes to infinity of 1 plus 1 over n to the n equals e. So here we have that our natural exponential function is of the form f of x equals e to the x with base e. And we can see that as as e is in between 2 and 3, the graph of the natural exponential function lies between the graphs of y equals 2x and y equals 3x, as we can see in this image here. Okay, so now we're going to evaluate each of these and round to 5 decimal places. So I'm going to go ahead and do that on Desmos. All right, I'm going to go to the scientific calculator, and then I'm going to have e, which is found in functions, e to the third power. All right, I get 20.08554 because I'm rounding to the 5 decimal places. And then I have part B, I have 2 e to the negative 0.53. I have 1.17721. And then I have e to the 4.8. And that's 121.51042. Alright, so now we're going to, so I have these values that I calculated from Desmos. Alright, and then now we're going to sketch the graph of each of these, state the domain, range, and asymptote. So for our first one, we have a equals f of x equals e to the negative x. So we could start with our y equals e to the x and reflect in the y-axis. So that means that we're going to have, by reflecting the y-axis, we're basically doing the opposite of our old x values. So since our old x was negative 1, our new x is going to be 1, 0 is going to be the same. Our old x was 1, our new x is going to be negative 1. Old x is 2, new x is negative 2. And then we keep our y values. So I went ahead and graphed those. And then we see that our domain is still going to be the real numbers. Our range, we could see, is between 0 to infinity. And our horizontal asymptote is y equals 0. Okay, so I have our next function is g of x equals 3 e to the 0.5x. So for this one, you could go ahead and calculate these values using a calculator, just plugging in different various x values. So here's a table of our x values and our y values that we calculated. And then our domain is going to be the real numbers. Our range is still going to be 0 to infinity. And then we can see that our horizontal asymptote is y equals 0. Basically, we don't have any negative y values. Here's application example that we could go ahead and do. So our example is the coronavirus begins to spread in Arroyo Grande, which has a population of 18,000. So after T days, the number of people who have succumbed to the virus is modeled by the function V of T equals 18,000 over 5 plus 1,245 e to the negative 0.97 t. Okay, so for A, we want to find how many infected people are there initially. So we can see that our t would be 0 because no time has passed. We're trying to find the initial amount. So I would get 18,000 over 5 plus 1,245 e to the 0. And you could calculate this on Desmos, and we would get 14 people because we're going to round down because we can't have 0.4 of a person. Okay, now we want to find the number of infected people after 1, 2, and 5 days. So I'm going to go ahead and do this on Desmos, but here's the answers that I get. Okay, so I have my equation set up here. So I'm going to calculate the number of infected people after 1 day. So I'm going to multiply that by 1. And I get 38 if we round that. After 2 days, I get 98 when we round that. And then for 5 days, I get 1,220 for 5 if we round. Alright, and then I'm going to go ahead and graph the function and describe the behavior. And I'm going to go ahead and do that on Desmos also. Alright, so here I have my function that we're going to graph. So I could see here that it just goes up, up, up. And then it keeps going up pretty high up there. And then it starts to flatten out at around 3,600 about there. So that's kind of like the cap of when it becomes a constant function, and that's kind of like where it stops increasing at that point. Alright, so now we're going to learn about continuously compound interest. So this is as the number of compounding periods increases infinitely as n approaches infinity. I forgot L there. So continuously compounded interest is calculated by the formula A of t equals p e to the r of t. So this is just, the interest is just always compounded basically. So our A of t is the amount after 2 years, p is our principal, r is our interest rate per year, and t is our number of years. So for example, we want to find the amount after 3 years if $1,000 is invested at an interest rate of 12% per year, compounded continuously. So I have P is 1,000, R equals 0.12, and T equals 3. So we plug that in, we get A of 3 is 1,000 to the E to the 0.12 times 3. And I get 1,433.33. So that's it for this video, and then I'll continue section 4.3 in the next video. Follow me there.